Hello and welcome to Project 152, your weekly specialist exam prep. Now every week we go through past questions from the QCAA. The plan is to get through every one of the 152 questions they've ever done. Now this is week 19 and we're going to go through these solutions. Now this is a tech active section, so make sure you've got your calculator ready because we're going to do lots of calculator stuff today. Let's go. Okay, so a fun little question here. Determine the time when the particle has a momentum of 620 kilograms. Now, momentum, we've got a formula for that. We can say momentum, which for some reason, let's use the letter P for it, is equal to mass times velocity. Now, we know the momentum, it's 620. We know the mass, 7 kilograms. Okay. And what does it say here? We want velocity. Now, I don't have a velocity function, but I do have a displacement function. So if I know a displacement function, velocity is going to be the derivative of that. The derivative of that function, right? And there's a specific reason why I've bothered to sort of write it in this very special way, because I want to use my calculator to do the whole thing. Okay, let's see what happens here. Let's get our calculator out. So here's my calculator, and I'm going to click Option because I want to do some calculations. So Calc, and I'm going to solve my equation here. So the equation is 620 equals, and then I have 7 multiplied by, and then I've got this derivative here, so I'll just use that one there, and then I type in my derivative. Now I'm going to have to do it with x's instead of t's. So 3x cubed minus 5x squared, oops, be careful, minus 5x squared plus 2x, and then minus 4. All right, last little bit here, we've got to go a little bit further. We've got to put a little x in there, and then close up our bracket that goes with the solve end. So the whole thing is we're solving 620 equals 7 times the derivative, and then we've typed in our function. Okay, and then enter. Okay, more solutions might exist. Exit. And we get two answers here, negative 2.59 and positive 3.706, 3.71. Determine the time when the particle has a momentum of this. We're told that time is between 0 and 10. So in this question, time cannot be negative. So we can disregard our negative 2.59. And so our answer is 3.706, which is close enough to 3.71. Now, may it have been quicker if, or maybe I didn't know how to use my calculator. I could have done this derivative by hand. 620 equals 7 times 9t squared minus 10t plus 2. But I really did want to show it to you, make sure that you got it. All right, let's celebrate. And next question. Okay, so this is a simple harmonic motion question, and I find that people really want to overcomplicate these questions, but they're actually relatively straightforward. If you just sketch them, graph them, and have a look at the graph, you can figure out everything from the graph. So that's exactly what I'm going to do. I'm going to sketch this graph. Well, actually, I'm not going to sketch this graph because this is the graph of displacement with respect to time. But I don't want to know anything about displacement. I want to know the maximum speed. So that's about velocity. So instead of graphing this function, I'm going to graph the derivative of this function. Feels a little similar to the last question, actually. All right, so we're graphing the derivative of our displacement function to get our velocity function. How are we going to do it? Option, let's see, calc, and then we're doing the derivative of this function here, 1.32, and then I need cos pi t on 2. Now instead of t, we're going to use x, and we need to make sure we're in radians mode because we've got this this obvious radian situation with the pi. So let's just type that in, shift pi, and then we're going to need an x, and I really should have done that beforehand. There we go. And then we've just got to make sure that we've got everything right here. Keep moving over the derivative, and then we need a little x in here. Okay, so we're sketching the derivative of it. Let's sketch that, execute, and we get this. Now this is telling our velocity at any given time. So the question is, what is the maximum speed of the particle? Well, we just need to find out how high this thing is here. So just looking at it, it looks like it's about 2. And so it looks like my answer is about 2.07, but we can do better than just about. So let's go G-solve here and let's click max. Okay, there we go. Now 2.073. Now technically I'm not looking in the right place at the moment because I'm in the negatives, and we can see here that time in this question is greater than or equal to 0. So I might just go across one. And here we are at x equals 3, which is time. At time equals 3, the maximum speed is 2.07. Now, interestingly, note that it says maximum speed, and I'm looking here at this like 3 value. There is another time. There are actually lots of times when it has a maximum speed of 2.07. If I do G-solve minimum, this, I know it's negative 2.07, but that's a velocity of negative 2.07. Speed is the absolute value of velocity. So that is a time also when our object is traveling at a speed of 2.07. So there's time 1, time 3, it's going to repeat. So time 1, time 3, time 5, time 7, all of these are going to have maximum speeds of 2.07. My answer is A. Celebrate. So here we are, we're looking at a exponential probability density function question. So there's part A, B, and C. So we're going to go through each of these in turn. Let's focus on part A first. Show that f of t is a probability density function. Now this question is strange and the marking scheme is strange for this. So let me break it down for you. What is this question about? Now a probability density function, we should know that for a density function to be a probability density function, the area under the curve needs to be equal to 1. Now, here we can see that the bounds for our function are t greater than or equal to 0. So let me write that down in mathematical notation. So here it is in mathematical notation. This is our probability density function, and the integral between 0 and infinity, because exponential probability density functions tend towards infinity there, needs to be equal to 1. I'll draw you a picture. Let's shade in this area. Between 0 and way over there somewhere is obviously infinity. The area needs to be equal to 1. Now, the question's worth 1 mark. As far as I can tell, if you wrote this, you get it correct. You could type it into your calculator, but your calculator doesn't allow you to put infinity there. So you'll just have to put in a big number. Not too big, because your calculator freaks out if you put a really, really big number there. But if you put in a decently sized number, you're going to get an answer that's 1 or very, very, very close to 1. I guess you can show them, talk to them about how you used your graphics calculator. But yeah, that's it. 1 mark just for showing that the area under the curve between 0 and infinity is 1. Okay, a bit of an anticlimax for that question. Part B is where the rubber hits the road. Let's celebrate still though. Part B. So part B says, determine the probability that a phone owner cracks the screen of their phone within 1 year. Okay, let's draw a picture of this so we know what's going on, what we're trying to... Actually, let's put it up here. So we've got here, we know that exponential probability density functions look something like this, and we want to know the probability, the area under the curve, between 0 and 1 year. Now, you've got to be careful because maths teachers love to turn these into tricks. I think this is a trick question, right? Because it says the time t in months. So our x-axis, which is time, is not in years. Our x-axis is in months. So if we want to know the probability that a phone owner cracks the screen of their phone within 1 year, we don't want to know within 1 year, we want to know within 12 months. boop, 12 months. So we want to know the area under the curve between 0 and 12. So let's write it here. The probability that someone cracks their phone between 0 and 12 months is equal to the integral between 0 and 12 of the function in question, e to the negative 0.16t, with respect to t. Okay, that is essentially the end of the question now. Because it is tech active, we just type this into our calculator and we get an answer. Now you can either do it in your graphing mode or you can do it in this mode. Now I'm going to do it in this because I've still got the equation there. I can just do it that way. So let's go option, and we're going to do some sort of calculation. We're going to do an integral, and we're going to be integrating this function wherever the letter E happens to be, shift E, negative 0.16, use X. Okay, and then we're doing it between, I think I need to go this way actually. There we go. We're doing it between 0 and 12. 0.85339, etc. Let's write that down. Okay, 0.8534. I've just rounded that 3 up, 0.8534. That's it. That's the whole question. It's a 2-mark question. We figure out what we're trying to come up with. Little trick with the months versus years. And then we just shove it into our calculator and we get an answer. Let's celebrate, and then the last question. All right, so the last question says 3/4 of phone owners take between 1 and m months before they crack the screen on their phone. Determine the value of m. You really want to draw pictures for these. So let's draw our picture. We've got an exponential probability density function that looks something like that. That's better. Now it says 3/4 of phone owners, so 0.75%, 75%, between 1 month and m months. We don't know what the m is, but we know that probability of it happening within that area is 0.75. So that entire picture is the setup, and now we just need to figure out or solve this for m. So let's write it up. The probability of it happening is 0.75, and it's calculated by finding the integral between 1 and m of the equation that we've got, 0.16 e to the negative 0.16 t with respect to t. And then we just need to solve this. And this used to be very scary when I was in school, but it's going to be much, much easier for you. All right, so here we are again, and we're going to ask our calculator to solve this for us. And what are we solving? 0.75, the integral, and you're going to have to pay attention here because this is a little bit confusing. 1, and then here we're going to write the letter m. Do I have an m here? Can I find it? There it is. See, it's there with the 7. So alpha m, like that. And then we can't use x. That's not going to work. We've got to use a different letter here, and I'll show you why that is in a second. 0.16, and then we go shift. Where's our e value? There's e, negative 0.16. And then we can't use t. We've got to use x here. There's x here. Okay, and then it's going with respect to x. Now, why can't we put x here? Because this x and this x are different, right? This is a variable, but this is like an unknown. This is a thing that we want to know. Usually when you use solve_n, you can just type in your equation, close the bracket, and you're done, because the calculator assumes you want to solve for x. It always assumes that. But here, I don't actually want to solve for x. I want to solve for m. So I'm going to do a little more work. At the end, once we've written out our entire equation, which I have made a mistake because I didn't put an equal sign in it. So let's go back here. Hope you were screaming at the screen here. 0.75 equals the integral between 1 and m, this. And then comma alpha m. Okay, and so the comma m says solve this equation, but solve it for m. Now execute. Now heads up, your calculator is going to think for a really long time, and you're going to think that it's broken. But it's just that we're sort of pushing it to its limit here, and it takes a little while. But so these are a very specific kind of question. They take a long time. I'm talking. It's still happening. It's still happening. Hopefully it spits out an answer soon. Maybe I should pause it and come back when it does. Still thinking. As soon as I press pause, it did it. So it takes a little while, as you can see. Let's press exit. And there is our answer, 14.2585. So we can write solve using graphics calculator. M equals 14.258 or 259 if I'm rounding. Determine the value of M. M equals 14.25. I don't need to interpret it as 14 months or whatever like that. I just need to say the value of M is 14.259. Now, of course, the solve-n doesn't inspire a lot of confidence because it takes so long to happen. You can double check your work, right? Because you can put that 14.25 back in here. 14.25. Put this in. When you type that into your calculator will straight away spit out the answer, 0.75, and you'll know you're correct. Okay, celebrate. Next one. So next up, we've got a fun little Simpson's rule question. We've got this dam. Now, it says it's like a top-down view, and it says this curve here is this function here. It's this ellipse. Not function, relation. It's an ellipse. Okay, the question is, use Simpson's rule with 4 strips to determine an approximate area of the surface of the dam. Okay, first of all, 4 strips. So what does that mean? Well, here's 0 right here. So let's put a 0 there. 0. And all the way down here, we're told that it's 6 kilometers long, so that's 6. Here, halfway, is 3. Here is 4.5. And here is 1.5. Okay, they're my 4 strips. Let me draw in my 4 strips. And we're going to use these 4 strips and Simpson's rule to come up with the area, or at least an approximation of it. Now, this is Simpson's rule as it appears on your formula sheet. It's big and it's scary looking. I prefer a simplified version of Simpson's rule, something like this. The area between A and B is equal to your strip width over 3 times the ends added together plus 4 times the odd added together plus 2 times the evens added together. I also like to put everything into a table so I can organize it, so I'm going to create myself a table as well. All right, here's my table. Now, whenever you do Simpson's rule, if you've got 4 strips, you're going to have 1, 2, 3, 4, 5 points, right? Because you've got the end one here, and then some in the middle, and then this end one here. You're always going to have one more point than strips. So 0, 1, 2, 3, 4, and always start at 0. Start counting at 0, don't start at 1. Otherwise, your odds and evens aren't going to make sense. They're going to be the opposite of what they should be. All right, the x values at these points are 0, 1.5, 3, 4.5, and 6. Now, these points, these are our y values, and we need to calculate them. We need to calculate this point, and this point, and this point, and this point, and, well, I don't think we need to calculate this point, right? That seems obvious that that's 0. So I'm going to have to calculate this one, this one, this one, and this one. And using my calculator is obviously going to be the fastest way to do that. So the way that I'm going to put this into my calculator is I'm just going to type this equation out. But before that, I'm going to ask my calculator to solve it. So option, calc, solve n. And then I'm going to type in this equation. All right, let me do that. Now, I've typed most of it out, but I haven't put in the x's and the y's yet. And there's a reason for that. I wanted to show it to you. So where the x's are, which is here, I'm not going to be typing x. Instead, I'm going to be typing what my x values, what I want them to be. So the first one I want it to be is 0. All right, 0 minus 2. I need to put a squared there. All right, so that's subbing in my x value. Now, this is where it gets confusing because where the y value belongs, I'm going to put an x, right? Because that's what I want to solve for. I want to sub this, put this into my calculator, make my calculator do the work for me. Let's solve that Okay, more solutions should exist. You can see it gives me two answers, negative 3 root 3 on 2 and 3 root 3 on 2. Why is it giving me two answers? Because our relation has an answer down here and an answer up here. I'm only going to worry about the answer up here, and then because ellipses are symmetrical, I'm going to find this area and then I'm going to multiply it by 2 at the end. So let's put in our answer, 3 root 3 on 2. So now that I've done that, I've really done the hard work, because now I can just sort of scroll back up again, replace the 0 with a 1.5 and go again, exit, and then I get this answer, 9 root 7 on 8. Wish I had a bit more space. I'll fix that up in a second. Now I can replace that 1.5 with 3 and execute that. And I can do 3 root 15 on 4. And then my last answer here, let's do that one, 4.5. Yep, 3 root 39 on 8. So now that we've done this, we can put it all into this formula here. That's going to take some writing out. Let's do that. So the area of the thing in question, or really half of the area and thing in question, because we're just doing the top half for now and then we'll multiply by 2 at the end. Half of the area is equal to the strip width, which is 1.5 divided by 3. And then we need to add our ends together. So 3 root 3 on 2 plus 0. 3 root 3 on 2 plus 0. And then we have to do 4 times the sum of the odds. Now the odds, you count here, 1 and 3. These are the odds. So 4 times 9 root 7 on 8 plus 3 root 39 on 8. Heading up here, but that's fine. And then 2 times the evens, and we only have one even, 3 root 15 on 4. Okay, that's it. Now, you should be able to type this whole thing into your calculator. You'll have to be careful with brackets and things like that, but then it should spit out a single answer. So I typed it all out. Just be careful with the brackets and all the rest of it, and I get an area of 14.84. So let me just write that down. Now, of course, I'm not quite finished yet, because that's half of the area. That's all of this. So I need to multiply that by 2. Total area equals 29.68. Nice to have some units on the end, kilometers squared. So that's the 4-mark question. We'll just get rid of some of this mess and then we'll tackle the last bit. Let's just celebrate that and then next bit. So part B feels relatively straightforward because we're saying evaluate the reasonableness of the approximation. Feels like we should just find the area exactly using integrals. So let's do that. The area is equal to, now we've got a nice little thing going on here. And in the same way that we had to multiply by 2, I think we're going to have to do that again because we're going to need 2 times this area here. Right? Okay. 2 times that area. Now that area is going to be between 0 and 6 of what function? Because that's not a function, that's a relation. So we might need to rearrange this so that instead of having the ellipse, the full ellipse, we have it as y equals something, and it's now a function. All right, let me write that down. So that's the relation that we've got a problem with, and we want to get y all by itself. So let's just leave y squared on 9 right here, and then we'll have 1 minus all of that. From here, maybe I can multiply both sides by 9, so then I'll just have y squared. Perfect, so y squared equals all of this. And now I can turn it into a function, y equals, just by square rooting both sides. Great, y equals the square root of 9 times all of this. Great, that is a function of y. And if you sketch that, what you'll find is that it's just this half of it, right? Because when I did that square root, technically, we've got a little plus minus here. The plus side of it is the top half. The negative side of it is the bottom half, but I'm only interested in the top half, so we'll go here. Great, I can use this now in my area formula. And now we can type this into our graphics calculator. So typing all of that in, I get an area equal to 30.3233, I guess, kilometers squared. Evaluate the reasonableness of the approximation. Approximation 29.68, exact value 30.32. Now when you're asked to do something like this, make sure that you make a statement. I think it's reasonable. These are very close answers. This was an approximation. This is our exact answer. So very similar, therefore reasonable. I'll go with the approximation is reasonable as there is approximately a 0.5 kilometre squared difference between this value and this value. Now the QCAA in their example said something like the approximation is reasonable as there's less than a 2% difference. But I think that all you really have to write is the approximation is reasonable and you'll get there. You don't even need to do this bit. At least that's what it looks like on their marking schemes. All right, let's go. And one more. So a question 17 here, a pretty tricky question, but they've been very kind to us because they've expressed this formula in a very particular way that's supposed to give you a hint as to what you're doing. Now, this should ring bells because we've got some kind of formula sheet going on. Acceleration is equal to all of these kinds of things, including v dv dx. So the acceleration of our object is given by this equation right here. But they've expressed it like this because they really want to help you out. So let's write it down and start working with it. All right, so we've got this beautiful thing here. If we look forward into the future, it says determine the velocity of the object when it strikes the ground. Striking the ground, like knowing where it is, that's displacement, which is x. So our equation here is in terms of v and x, but it would be nice if it was just a simple equation without like derivatives and stuff in it. So how are we going to do that? Well, first of all, I'll divide both sides by v. That'll just give me a nice little dv dx. Okay, so far so good. Now, you're used to, in methods, having something like dy dx equals, and then something like x cubed plus 5x squared. This is not behaving like this, right? Because the v is on the top, but here, the v is in the function. Here, the y is on the top and the x is on the bottom and the x is in the function. So let's flip everything over so it's behaving appropriately. That's much, much better now because now we can work with it in the same way that we would work with dy dx and then a function in terms of x. This is dx dv and a function in terms of v. So if I want to know what x is, I just integrate this. Now it can feel very confusing about how to integrate this, but there is a nice little integral that you've got if you have an equation in the form f dash of x over f of x. And you can integrate this really nicely. Now this almost looks like this, right? We have a function on the bottom, which is a quadratic, and we have this function on the top, which is linear. Now, the derivative of this, if this is f of x, the derivative of this is negative 0.008 v squared. So I really want the top of this to be negative 0.008 v. Why don't I just make it that? Well, that's great news because now that works exactly like how this is shaped, so that's good. But you can't just randomly add in a negative 0.008. You can't just randomly multiply by things just willy-nilly. But if I do something extra clever and put a 0.008 out the front, a negative times a negative is a positive, and negative 0.008 divided by 0.008, I'm really just multiplying by 1. So problem solved. I haven't changed anything at all, but I've changed the most important part of this, which is now this is behaving in this way. Now it is possible you're not familiar with what happens when you've got f dash of x over f of x. Very, very straightforward. It's ln absolute value f of x, and of course a nice little plus c on the end. So I've still got this negative 0.008 here. Too many, not enough maybe. 0.008, multiplying that by ln absolute value 9.8 minus 0.004 v squared. And of course, don't forget your nice little plus c on the end. So now I have an equation, x equals negative over blah, 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 blah. Now, how do I find that c value? Because I've got a relationship now between x and v. If only I knew the c value. So let's look back at the question to find some sort of initial values. All right. An object is released from rest at a height of 100 meters above the ground. Now, I'm going to admit that I've made this video and gotten it wrong because I read this and I jumped too fast to the answer. So let's read it and make my mistake. An object is released from rest. Okay, so if you drop an object from rest, its initial velocity is 0. So when v equals 0, that's not my mistake. At a height of 100 meters above the ground. So I saw that, and I also saw that x is the displacement from the ground. And so I said, oh great, x is 100 meters above the ground. I'll say x is equal to 100. And this was wrong. Now, why was it wrong? Let's look here. We have this phrase, the motion of the vertical descent of the object. And it says that acceleration is equal to positive 9.8. That means that the motion, the positive motion of this object is taken to be going downwards. So, if we sort of work backwards from there, we need above displacement to be negative 100. And we're moving towards the ground, and the ground is 0. So we're not there and falling away from some place. We're moving towards this thing, and everything's being reversed because we're not using negative 9.8 here, we're using positive 9.8. Very tricky stuff, but that's what we're going to have to put in. All right, so let's sub in velocity 0 here and displacement negative 100. Just a heads up, I've done a couple of things here. X is negative 100. Instead of writing negative 1 over 0.008, I just wrote negative 125 because they're the same thing. And now here, this bit here, where I put velocity 0 in, I can simplify this straight away. Let's just make it easier. This is 0. So this is just going to be the absolute value of 9.8, which is just 9.8. So we can just have ln 9.8 there. All right, so I've just typed that into my calculator, solve in 185.298. That means that we have a full equation. Let's write it out. X equals negative 125 ln 9.8 minus 0.004 v squared, and then a nice little plus c on the end. Just go away, calculator, please, which is 185.298. Okay. What have we got? We've got displacement equals some function of velocity here, and then we're told determine the velocity of the object when it strikes the ground. So striking the ground, let x equal 0. So 0 equals this equation. All right, so I have put it into my calculator. This question is full of surprises. So when I solve this, 0 equals blah, blah, blah on my calculator, let's take a look at what I get. Heaps of solutions. Well, not heaps, 4. Negative 59, negative 36, 36, and 59. So 4 solutions. But 4 solutions makes no sense. An object is dropped, it falls towards the ground. We're trying to find the velocity when it hits the ground. There is only one answer to this question, or at least there should be. So what can we get rid of? Okay, the motion of the vertical descent of the object. This question, we've talked about this 9.8 being positive, so velocity here is a positive value. So we can ignore the negative solutions here. It has a positive velocity. The velocity is being measured in a downward direction, not an upwards direction. So it's either a velocity of 36.73 or a velocity of 59.58. So which of these two answers is correct? And this is why sometimes using solve n can lead us astray, And I think a better way to do things is sometimes to graph things, which is what I've had to do after doing this little solve. All right, so I have my calculator up. I'm sketching this as y equals blah, 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 and there's an x here, right? Now, let's draw it, and we get this weird little thing here going on. Now, you need to be sort of thinking about what's going on. There's no time on this graph. We have velocity on the x-axis, and we have displacement on the y-axis. Displacement is negative 100 when velocity is 0, right? So this is when we drop the hammer and then it starts falling towards the earth. I know it looks like it's moving upwards, but remember we reversed everything with this 9.8. It's falling towards the earth, it's falling towards the earth, and this is where it hits the earth with whatever that happens to be. So we can do a G-solve here and do a root and go to the other side. This is our answer. It can't like continue through the earth and then turn around and come back down and hit the earth from the bottom. This is an artifact. This is nonsense stuff. This is the value we need. It's 36.73. So there's our answer, and we can make a little note, rejected negative, since, where is it? V is always greater than or equal to 0. And we rejected that superfluous one as well. Some calculators won't even come up with that superfluous answer, so 36.73 is our final answer. All right, that is Biggin celebrating done. So that's it. That's week 19. Go to the link in the description. You'll find the week 20 questions and you'll have a week to do them. Thanks for sticking around until the end if you've made it all this way. This is probably the longest Project 152 we've ever done, but some pretty interesting questions in there. Catch you next week.